Hey there. Now that we've learned how to expand logarithms, we're going to go the other way. We're going to combine them. So same rules, but you've noticed I've written them in a different order. I've written them in the way that we can combine. So when we see two logarithms with the same base that have been added, or two logarithms have been subtracted, or a coefficient in front of a logarithm, we can combine those into a more condensed version of a logarithm. Two logarithms being added can create one logarithm that has a product in that argument. Subtraction creates a quotient inside one logarithm, not two logarithms being divided. That's really important. And a coefficient can be moved as an exponent, just like before we moved an exponent to a coefficient. So we're going to practice that. This is very, very useful for what we're doing when we solve some equations that have logarithms in them. It's really, really useful to be able to combine those things. It's important we have to be able to do it. So that's mostly why we're covering this right now. So let's get started. Just like in expansion, you'll look for what's connecting that logarithm. We're going to basically undo that idea. So we separated products and quotients typically first and then exponents last. We did have some options in there, but in this case, we really don't have any options. There's one order in how you combine logarithms. Number one, you take any coefficient that you have and you move it as an exponent in whatever that logarithm, whatever's inside of that logarithm. So we're going to take a look, move our exponents first. After that, we combine any logarithms that have the same base that are being added or subtracted. So let's take a look at our first example. Number one thing, when we notice we have coefficients and we have logarithms of the same base and we're asked to combine these things, move your coefficients first as exponents. So that means we have log base 3 of x to the 1/2 power minus log base 3 of x to the 3rd. That's our first step every time. After that, we look to see if we have added or subtracted logarithms. Since we have a subtraction, we're going to create a quotient inside of one logarithm. That's really important. What we don't do, we don't have a logarithm over a logarithm. That's not correct. This doesn't say that we have log a of m over log a of n. It says log base a of m over n. You see, why it's so important is we're going to have the change of base formula in the next video where we do have a logarithm over a logarithm with the same base. That's a different thing that we're going to do with that. So since we have log base 3 minus another log base 3, we can create one log base 3 with our two arguments of our logarithms being divided. Now, once we've done that, it's very, very important for us to be able to simplify this. So when we simplify, when we have common bases being divided, you're going to get this most often when you have subtraction two logarithms, you need to simplify. So 3 minus 1/2. Now you can do 1/2 minus 3, get a negative exponent, move back down to the denominator, that's fine. But 3 minus 1/2 is going to be 2.5 or 5/2. So we're going to get 1 over x to the 5/2. If you needed to do 1/2 minus 3, change it back into 1 over x to the 5/2 to get that, that's perfectly fine. Lastly, sometimes you'll be asked to write this as a radical. So x to the 5/2 power creates log base 3 of 1 over, that's a square root with x to the 5th as its radicand. You should put parentheses around this so that we are not confused that that is outside some logarithm. That's it. So we can combine this as log base 3 of 1 over square root of x to the 5th. Should we rationalize it? Maybe. We could be asked to do that. Sometimes we can leave it, sometimes we can't. It really depends on what you're doing with it. I'm going to leave that, but if you had to rationalize it, you could multiply, well, you could simplify this. I guess I'm going to show it to you. X to the 5/2 power is x squared with the square root of x. Rationalizing means take the radical part and make the power match the root on the denominator. We'd have to multiply by a square root to do that. This would give you an x squared. Square root of x times square root of x is x. And so we would get square root of x over x cubed inside of that logarithm. That's as complete as I can make this problem. Really, we could probably end it here, but I want to show you some other options of how you could see this. So if you get this, and your answer looks like that, and you go, what are you wrong? Nothing. They're just manipulating a little bit. They're saying x to the 5 has power is the square root of x to the 5th. I can make x squared and have an extra x in there. Simplify both those, you get x squared square root of x. I can rationalize the denominator and end up getting square root of x over x cubed. That's really all that is. The primary thing I'm trying to teach you is how to get from here to here. That's the idea. Let's move on a little bit. So the next one, we're looking at this, we're asked to combine, we see a log base 4 and a log base 4. The first thing we do whenever we're combining logarithms is we're going to move our coefficients as exponents. Now we don't have one here, but we do have a 5. Do you move the 5? Do you move the negative 5? Well, you can move this as a negative 5 and change it to a plus and then multiply logarithms together. It's really easiest to move the 5 and subtract. You're going to get the same thing. It's a lot easier to do. So don't mess around with moving this with the sign. Unless you only have one logarithm and it is negative, sometimes we can do that and it's helpful. But in general, just move this as a power 5. So we're going to do that first. Notice what we're not doing. We're not factoring first. This is the literal opposite of expanding logarithms. In expanding, we factored everything first, and we use that to create these products. Well, here, when we're going backwards, we're going to factor last and use it to simplify whatever our quotient is. Remember that 5, because that's an exponent, it needs to be an exponent on that entire expression. So x minus 1 all to the 5th power. Now what we're going to do is we're going to look at whether we're adding and subtracting. Since we're subtracting here, we're going to create one logarithm with a quotient. So I'm going to get to this when we get to that example and the one after that. Every positive logarithm or logarithm being added is going to create a factor on the numerator for you. Every logarithm that's being subtracted or negative is going to create a factor on the denominator for you. You should do this all in one step. Don't do it like 5 different steps. Do it all at once. Positive logarithm, that factor goes in the numerator. Minus or negative logarithm, same base, that factor goes on the denominator. And now we have to simplify. So now's the time where we factor and see if anything cancels out. So x squared minus 1 factors as x minus 1 and x plus 1. Well, that's something that we can simplify. Since we have an x plus 1, x minus 1 over an x plus 1 to the 5th power, this factor and one of those factors actually do simplify. So we end up getting log base 4 of x minus 1 over x plus 1 to the 4th. A lot of students get here and they leave it because they forget to check that. The reason why I'm showing this problem to you is so that you do check your simplification. It's the literal opposite of your expansion. And so when you get down to the end, you got to factor and check to see if you can simplify. It can happen a lot when we're combining some logarithms. So we're taking a look, we're saying exponents first. So move those coefficients as exponents. Every positive logarithm creates a factor on the numerator, or added logarithm creates a factor on the numerator. Every negative logarithm creates a factor in the denominator. Every subtracted logarithm creates a factor on the denominator. Just put it all together. And since we've dealt with exponents first, we don't have to do anything else besides simplify at that point. Okay, moving right along. So we got another one. We're going to combine this. First thing we do is we look for any exponents or any coefficients that move as exponents, and we don't have any. Well, that's okay. What we're going to do now is notice that because these all have the same base of e, they're all natural logarithms. We can combine this with products and quotients in one logarithm, one ln, not 3 different ones. We're trying to get one, and so we're going to create one quotient. Every logarithm that's added or positive is going to create a factor on the numerator. every logarithm that's negative or subtracted creates a factor on the denominator. So we just got to look at this and say, because they all have the same base, because we're adding and we're subtracting, we can connect by multiplication and with division. And so we're just going to notice where those things go. So create one logarithm, create a big fraction. All of the factors of these two logarithms, so ln of x over x minus 1, well, that's positive. That's going to create this as a factor on the numerator. Plus, okay, plus means I'm connecting by a product, plus product. This should create a factor on my numerator. Now, it is a factor. We are multiplying there. Minus, okay, when we subtract, or we have a negative logarithm, when we're combining via subtraction here, we're creating a factor on the denominator. Whatever's being subtracted, that creates a factor on your denominator, just like the positive created factor on your numerator. So we're going to put this as a factor here. Man, I hope that makes sense. I hope that you're seeing that. Addition, positive numerator, subtraction, negative denominator. We're combining at one time. We're just using these two properties at once to create this quotient that has factors appropriately depending on whether we're adding or subtracting. We're doing these properties, but it's nice to do them at one time so we don't get confused with different steps and where you go. That's harder to do. Well, now we have to simplify. We didn't factor at first, we didn't have to. But now, after we've combined via products and quotients, depending on whether we have addition and subtraction, we've got a factor and we have to simplify. So we're going to do that. And writing it that way also might help you to see that we can simplify sometimes. So x on the numerator, x on the denominator, we're multiplying fractions here. We could write one fraction. That simplifies, and that makes things a little bit nicer to see even. Now that is a complex fraction, and how we simplify complex fractions is typically we multiply the main numerator, this part, and the main denominator, this part, by whatever the LCD is. So in this case, the LCD comes from whatever your complex fraction is. So we take a look at that. That's x plus 1 over x minus 1. Our LCD is x minus 1. If we multiply both the numerator and denominator by that LCD, it's going to simplify the denominator of a complex fraction. That's usually what happens. There are other ways to do it. I like this technique. It works, in my opinion, the most concise, but you can do it other ways. So in this case, we say, all right, we multiply by the LCD. LCD always cancels out the denominator of our complex fractions. It doesn't cancel out anything here. This is on the numerator. The only denominator here is 1. The denominator here is where we got our LCD from, the x minus 1. This goes away, so that's going to cancel. We're just going to get x plus 1 over whatever this is. All right, well, when we don't cancel this, this is going to end up giving us x minus 1 squared times x plus 1. And we're going to see one more thing. So, cancel here. LCD does that with complex fractions. X plus 1, we got it. X minus 1 times x minus 1. This is not on a denominator. This is multiplying right to it. That's going to be x minus 1 squared. And x plus 1. And then we see, okay, we have a factor over a factor. Everything's multiplied together. It's all factor. It looks really good. This is also going to simplify. Leaving us with 1 over x minus 1 squared, and that's as simple as we can get it. So ln of 1 over x minus 1 squared, wow, that's a lot nicer to work with than that is for most of the things that we're going to do, especially if we have to solve anything with an equation, because you're going to have to combine those anyway. So we're really going opposite. We're moving our exponents, the coefficients and exponents first, combine everything at once. All of our subtraction and addition creates corresponding factors in one logarithm of numerators for addition and positives and denominators for subtraction or negatives, and then we factor and simplify. That's actually the hardest part is, okay, so you're factoring and you're getting rid of the complex fraction and then you're simplifying more. That can take the most work. All right, moving on just a little bit. We got two more examples. This next one, just a little bit of work of simplification here that I want you to see. Also that when we have multiple things that are being added, subtracted, we can just group those together as products on numerators or products on denominators, depending on whether addition or subtraction. So let's take a look at it. First thing, whenever we're combining, let's move all of our coefficients as exponents first. So that's going to be log base 3 of, you can also choose to write these cube roots as exponents themselves. That'll make it nicer if you have to move other exponents because you can multiply them a little bit nicer than you can with an actual radical. So log base 3, great. Let's write that as x to the 1/3 power. So this is x to the 1/3 power, but when I take that 21 as an exponent, now hopefully you see what I'm saying. It's a little bit nicer to think of 1/3 times 21 than a cube root to the 21st power. That's a little bit more awkward for some people. Log base 3 of 9, question. Could you change that? Could you simplify that right now and do 2? Because log base 3 of 9 is 2. 2 to what power gives you 9? 2. Could you do it? Yes, and you could, but you wouldn't be able to combine it with the rest of these logarithms. So if our goal is to get one logarithm, you don't want to simplify it. If that's not our goal, maybe you would in some cases, but right now we're trying to combine this into one logarithm, and so we're not going to simplify that. I hope that makes sense. We do need to move that 2. And this doesn't have any exponent for us. Another thing that you could see, hopefully you do see it, could you just take log base 3 of 9 and log base 3 of 9 and subtract it? Yeah, you could. And sometimes books do this and we don't catch it. And we go, well, wait a minute, could you just get rid of that? Yeah, you can, but I want to show you what's going to happen because sometimes we can see this or miss it, but later on we'll see that it simplifies. I want to show you right now, whether you subtract them here or whether you create one fraction and simplify them in the fraction, it doesn't matter. Now that would be quicker, what I just talked about, but I want you to see the point of putting this together in one fraction and using division to simplify it. That way we kind of validate that that's possible there. So I want to see that. So we've moved our coefficients as exponents. We know that we could simplify this to do 2 and 2 here. Hey, 3 to what power gives you 9? 2. 2 minus 2 is 0. Great. Could you do log base 3 of 9 minus log base 3 of 9 is 0? Yes, you could. Could you make this one fraction anyway if you missed it and get the same answer? Yeah, there's lots of options. As long as you're following the properties that I've given you, you really can't get it wrong. So we know that if we want to combine this into one logarithm, it's going to be a log base 3. It's going to be a fraction because we have both positive and addition logarithms and subtraction or negative logarithms. Every one of the logarithms that's positive or being added creates a factor on the numerator. So I'm going to have a factor of x to the 1/3 to the 21st power. Now, could you right now simplify that and say 1/3 times 21 is 7? Absolutely. And that's exactly what we're going to do. So this is x to the 7th power. 1/3 times 21 is 7. Times, because we're adding, addition creates products. X to the 7th power times 9. Addition creates products times x squared. Subtraction creates factors on the denominator, quotients for us. So minus log base 9, that creates over 9. And check out what happens. Whether you simplify here or create 2 and 2 and simplify there, or 9 divided by 9, you need to be able to see that we are simplifying that. That would create 1. If we further continue, now we're just going to combine some common bases by multiplication. That means we're going to add those exponents. Log base 3 of x to the 9th power, that's as simple as we can make it, as combined as we can do. I hope it makes sense. I hope I'm really making it sink into your head about how you connect some of these factors as products and quotients, depending on whether they're added or subtracted terms. We're going to come back with one more. I'm going to make it as crazy as I can, and then we'll go through it together. All right, so that's about as much as I could think of before I ran out of space on the board, so let's go ahead and do that one. If we're going to combine some logarithms, and it's very important to do this in a lot of cases when we're solving equations, is you need to get one logarithm. We're always going to move coefficients and make them into exponents of whatever our factors are inside of our logarithm. So we're going to take a look at this and move every single one of those coefficients, not the signs, just the numbers. So that's 2 as an exponent, 1/4 as an exponent of x minus 1, 2x plus 3 to the 3/8 power, minus log of x to the 1/5 power, log of 2 to the 4th, and then, hey, that doesn't have an exponent. Log of 12. Now, we are going to combine all of this at one time. Because these are all logarithms of the same base, and they're being joined together by addition and subtraction, we're going to create one huge fraction. And then we're going to go through, and depending on whether we're adding or subtracting, we're going to organize these factors in the appropriate numerator or denominator. So positive says, I'm going to put that factor on the numerator. Minus says, I'm going to put that factor on the denominator. Plus says, I'm going to put that factor on the numerator. Minus says, I'm going to put that factor on the denominator. Minus says, I'm going to put that factor on the denominator. And plus says, I'm going to put that factor on the numerator. Could you do it differently? Yes, but I've never seen a more concise way to do it. When we understand that addition creates products, these are all products. Subtraction creates quotients. That's a quotient, that's a quotient, and that's a quotient if I were to expand this. Those are all on denominators there. That's the easiest way I've ever seen how to do it, or created how to do it. Now what we're going to do is, if you have to, you can write these as radicals, so I'm going to show that to you. There's not much to simplify except for this right here. You should expand that and say that that is 16. 12 over 16 we can simplify. So I'm going to write this 12 first, change that into 16, and organize it a little bit better, and also write these as radicals. So 12, we got it. 16 is here. I'm going to have x plus 1 to the second, and I'm going to write this as an 8th root of 2x plus 3 all to the 3rd power. If this is in parentheses, that has to be in parentheses too, if you have a power that's greater than 1. So we have 3, we got to have 8th root, that's power here, root here. So 8th root of 2x plus 3 to the 3rd power. Our numerator looks pretty good. We're going to simplify this in a moment. All the things I'm going to do, since I took that as 16 here, I typically write single term factors before any multiple term factors. So that's a 5th root of x. Then a 4th root of x minus 1. We don't need parentheses here. And the only reason why we don't is because that's a power 1. That's a radical 4 and a power 1. So 4th root of x minus 1 to the first, you don't need parentheses. We're going to simplify the 12 and the 16. 4 goes into 12 3 times, into 16 4 times, but nothing else really simplifies. There are ways that you could combine these radicals, but it becomes pretty cumbersome, and it's not going to be generally any better for you. You can do it. If you have to, you have to. But I'm going to leave it this way. All right, that's about as good as I can see how to combine that. I hope that that makes sense. We're going to see this in just a couple videos when we start solving logarithms without common, actually with and without common bases. We do this in both cases, and also in calculus we see it from time to time. So I hope that, that you enjoyed the videos. I will see you in a little bit for a change of base, and then we get into solving.